Welcome back. In the previous video, we did some fairly involved math to derive the actual functional form for the Logit probability. And now we're going to use that derived functional form of the Logit probability as well as data on decision maker attributes and attributes of the choices, as well as the observed choices that were made. And we're going to combine all that information and show how we can actually estimate the preference parameters that we can use as the basis of counterfactual simulations. So let's consider the model that we had before with differenced u's as a function of differenced betas and x, and then gamma times differenced z's. The things that we can observe in this equation are x, z1, and z2. Another piece of information that we would have in our data is the actual decision that was made. So did the decision maker in this case choose option 1 or option 2? And we're going to call that di. And we can mathematically express these observed choices in two ways. So we can use di, which is an integer variable that takes on values 1 through j, where capital J is the number of options. So in this case, capital J is 2. We can also express it as dij, which is binary, which just says was j chosen. And we'll see how this expression of the observed choice helps us mathematically moving forward. If we assume that the epsilons are IID type 1 extreme value, then that's going to give us the choice probabilities that we derived in the last video. And in particular, because we're dealing with differenced utilities, we're going to have a 1 in the denominator for the differenced option. So the differenced option, it's exp of ui2 minus ui2 is just exp of 0, which is 1. And then we have the differenced option for pi1. So if these two epsilons are type 1 extreme value, then their difference, or epsilon tilde, is going to be distributed logistic. So that's why if you've ever worked with the logistic distribution, you'll see that this makes a lot of sense and is hopefully familiar. So given this formulation, we can view the event that di equals j as a weighted coin flip. And then this is going to give us a random variable that follows a Bernoulli distribution. And that's going to make it simple for statistical modeling. So now let's think about the likelihood function. So just as a brief review, the method of maximum likelihood estimation says, I'm going to assume that the data is generated by some true model, and then I just want to use the data to tell me what are the parameter values of that true model that are most likely to give rise to the data that I just saw. So in this case, our true model that we have in mind is the Logit choice probability coin flip weighted, and we want to estimate the gamma and the beta that would give us what we see in the data as a result of that weighted coin flip. So we take all of the decision makers in our sample and we take the product of their Bernoulli likelihood functions. So this is just the Bernoulli likelihood where it's p to the d times 1 minus p to the 1 minus d, but here we've substituted in option 2 for that. But we can express it in this way, and this is maybe more familiar if you've seen the Bernoulli distribution in a prior statistics class. And then if we want to get crazy, we can actually plug in the formulas for the utility differences as a function of the parameters. So in the end, our likelihood function has x's, z's, and d's in it, as well as other mathematical functions like exponentials and fractions. And then we want to estimate beta 1 minus beta 2, so that's one parameter that we can estimate, and then gamma is the other parameter that we can estimate. Now, typically, we want to maximize the log of the likelihood instead of the actual likelihood. There's a lot of reasons for that we don't need to cover in this video. But if we take the log of that prior formula, the log of a product becomes the sum of the logs. The log of an exponentiated expression, you bring down the exponent and multiply it by the log. And so everywhere we had a multiplication operation becomes a summation operation now. Everywhere we had a exponentiation operation, we brought that down and multiplied it. And if we want to be very compact, we can just say this is the sum over the i's and sum over the j's of dij times log of pij. So then we can expand this out if we want to. And it can be helpful because there's some like terms that we can consolidate if we do it this way. So all I did was just plug in the values that we got here, given the formulas. So what's the log of a fraction? Well, it's the difference in the logs, and that's the key thing here with the log of P1 and log of P2. So hopefully you can see that this was the numerator of P1, and this was the denominator of P1. I've taken the log, and then the fraction or the division becomes a negative or a subtraction. And then we can kind of see there's some simplification options here. So I can cancel out the log and the exp here. I can consolidate these two terms that are in the denominator of both probabilities. And then I can get rid of log of 1 because that's 0. So once I do this, I get di times the difference to utilities minus the log of 1 plus the exponential of the difference to utilities. So this is a very compact formula that is basically arising because of the simple Logit probability formula, as well as the fact that the probability has a ratio in it that turns into a subtraction. So importantly, we only need an indicator for if option 1 was chosen, and then everything else is just x's, z's, and then the parameters that we want. So we can actually substitute in the actual expression for the utility, the difference utilities, and then it becomes this fairly simple formula, and then we can estimate this difference beta parameter as well as gamma using any kind of nonlinear optimizer that we would choose. These are widely available in any modern statistical programming software such as Stata or R, Julia, or Python. So that is how we take our Logit probabilities to data, and this is where all discrete choice analysis starts. We start with the Logit, and then maybe if it's not realistic enough, or if it has some drawbacks that are too big, that are too large for our setting, then maybe we do a different approach. But basically, the likelihood function that I just showed you is programmed in and widely distributed and optimized in any kind of software that you might want to do statistical estimation in. And basically, when I say nonlinear optimization, that just means the computer's going to guess and check different values of these parameters and then figure out which one is going to yield the maximum of the objective function that is being maximized, which is the likelihood function. In our next video, we'll talk about how we can extend this to more than 2 choices. So I hope to see you there.